This last segment will be on determining stability and attraction for a given fixed point. We actually, of interest really is not so much determining stability, but actually determining instability. So it's determining attraction and instability. So let's give again a simple definition. Remember, we're talking about a fixed point of a dynamical system. So x tilde is a fixed point. And we say that that is unstable. Sorry. So it is unstable, quite simply, if it is not stable. So you either get stable or unstable, and we will be interested in the case of unstable. So we're going to look for criteria for unstable, for critical point being unstable, criteria for 1, instability, and 2, attraction. Okay. And the idea is to use the linearization of the equation at the fixed point. So we use linearization of the equation at the fixed point. The equation at the fixed point. Okay, so if the equation, let's write the equation here, x dot is equal to f of x. Fixed point is determined by f of x tilde is equal to 0, right? And this whole thing is going to lead to the linearization of f at x tilde. So that's df at x tilde. So it's the derivative of f at x tilde, and the claim is that encoded in this is the stability information that we want. Okay, so how's that going to go? Well, let's talk a little bit about what df of x tilde is. So, you know, when I write the equation x dot is equal to f of x, remember that x is an element of U, which is a subset of Rn, so that means that x is actually a vector, x1 up through xn, but f goes from U into Rn, so it takes values in Rn too, so f, the values of f, is really a vector too. Let's call that f1 up through fn. So i.e., each fi here is a function of x, and then that will be equal to fi of x1 up through xn, just belaboring the notation. So we could rewrite this equation here, bring that down here, and rewrite it in this sort of not very compact form of x1 dot is f1 of x1 up through xn, x2 dot is f2 of x1 up to xn, and then this would go all the way down to xn dot is equal to fn of x1 up through xn. All right, so given writing the system out in this equations, then we can explicitly say what df of, and that's going to be called the Jacobian. Right, so this is the Jacobian. This is the Jacobian. That is df at x tilde, and this is going to be an n by n matrix, and it's basically just given by the partial derivatives of the different components of f with respect to the different variables. So the first entry is df1 dx1, then along this first row are the derivatives of f1 with respect to the various x's. Down the first column are the derivatives of the different components of f with respect to x1, And then finally, obviously, you finish with dfn by dxn. So it is that n by n matrix, and that's called the Jacobian. So what we know is that stability is determined in many cases by the eigenvalue structure of this matrix. So note, very importantly, note this is a constant. This is what's called a constant coefficient matrix. Constant coefficient matrix. So that's because we have evaluated, because the entries are evaluated at x tilde, evaluated at x tilde, right? So it's actually, so it's constant, right? So we get stability and instability in terms of this matrix A. So here are the criteria then that we want, and that is that one is that x tilde is unstable if there is an eigenvalue of this matrix, an eigenvalue of this matrix df at x tilde with a positive real part, with a positive real part. So what you want to think of is that imagine df was actually diagonal, right? And then the eigenvalues would be on the diagonal, having positive real part would be then that you had, and imagine they're real, then it would be that you have a positive number somewhere on the diagonal. It's a diagonal matrix, so you would have xi dot is equal to lambda I, say, times xi, and lambda I would be positive. Then you would have growth like e to the lambda it, so you'd have exponential growth. So that's why that's true. Okay, so secondly, we want to say that x tilde is attracting. This is a criteria for attracting if all the eigenvalues, of df at x tilde have negative real part. Negative real part. Okay? So what's happening then is that if all of the eigenvalues are to the left, that corresponds to decay somehow, and that means then that you have sort of attraction, and so on. So this has given us now a criterion for attracting and a criterion for instability that are somehow complementary to each other, and those are the two important things that we'll need and use.